Good afternoon. Very welcome. I find it a little bit ironic that that watch is not showing the correct time when we are going to hear about the best clock in the world. But that's life. I'm very happy to welcome Martin Zelan. He has a background in laser physics with a PhD from Umeå University. Has, among other things, worked with laser-related quantum information at the National Institute of Standard and Technology in a very famous group, I should add. And is now at the, I don't know how you want to present your institution now since you're changing name, but the more famous name is SP, the Swedish Technical Research Institute for Standard and Metrology, something. So I hope you will enjoy it.
Yeah. Thank you very much for the introduction, and thank you so much for inviting me here. It will be a pleasure to talk about kind of my favorite topic. It says how to build the best clock in the world, but I would say the presentations is very much about how to measure things, and how to measure things very, very good. So on that topic, I will also try to kind of cover the basics of metrology. Do all of you know what metrology is? It has nothing to do with the weather. It's sort of the science of measure. I will also cover some basics of a few Nobel prizes, which is needed to build the best clock in the world. So we have quite a challenge here. I have a challenge and you have a challenge, because I'm going to cover a lot of things, including Nobel prizes. So I would say most of the slides in this presentation you can make to 1-hour presentations. But I'm going to try to be general and give you the overview of the entire field. So what I'm going to do is I'm going to introduce myself, kind of what Per-Erik just did. But then I will talk about the background and the importance of measurement. After that, I will go into the main part of the talk with a little bit of history of time measurement, how time has been measured in the past and how it's defined and so on. Then I will talk about laser cooling, which sounds really, really cool, right? You know what it is? You will in a while. And then finally, I will talk about optical frequency measurements, which is essentially an optical clock, which is the best clock in the world at the moment. But a little bit about myself. I'm from the northern part of Sweden, in a city that's called Örnsköldsvik, meaning I don't want to talk about ice hockey today. We have a team which is doing terribly at the moment. But I took my master in physics at Umeå University. I took my PhD in physics there as well. Laser physics, experimental physics, very related to laser cooling, which is the fundamental principle of how these clocks actually can work so well. Also during my PhD, I worked a little bit at NIST. And as Per-Erik said, NIST is the National Institute of Standard and Technology in the States. It's huge, but it's very closely related to what SP is in some way, because they are also responsible for the SI system, like the meter and time and so on. So that was actually the reason why I got to know about SP from my time there at the States. So, but for the last 5 years, I've been working as a research scientist at SP, and what is now to be called RISE. And I also added these 3 letters here, which means National Metrology Institute. So SP RISE is a very, very complicated institute at the moment, but I identify very closely to the NMI part, the National Metrology Institute, where we are responsible for the meter, for the second, for the pressure, and for, all these kind of units that is very, very important when you do measurements. So if you want to do very nice measurements, you can contact us. We can do the measurements for you. But maybe more importantly, we can provide what is called a traceability, a stamp on your measurements, verifying it. That's kind of okay. But NMI, and why is an NMI important? So I will start with a little bit of a funny slide here. Do you recognize any of these pictures? Do you associate them to anything? Yes. Well, we can start with the top right. It is supposed to be the Mars Climate Orbiter. Have you heard about that? Well, I wouldn't say fun story, but it's a story at least about how scientists in Europe and how scientists in US failed to do the calculations from metrical units, that's meters and so on, what we're used to, and to empirical units, inches and feet and so on, with the result that this climate orbital came too close to Mars and actually burned up. And even though it doesn't really have anything to do with measurements, it kind of tells you what's important, that is, if you want to do something that is that expensive, you want to make sure that you're doing the correct calculations, measurements, and put all the correct stamps on it. So that's one example of why NMIs are needed and why NMIs should have been involved in this project to begin with the standardizations of units. This one, you know what that is? It's the Hubble Telescope. There's a similar story there, that when they launched this telescope, which is an amazing scientific instrument, when it went up in space and started taking pictures, all the pictures was fuzzy because the lens was manufactured incorrectly. The lens was actually 2.2 micrometers too thick, meaning all the pictures of the galaxies and whatever was fuzzy. They managed to fix it by sending up a pair of glasses to it, actually. But still, a very sort of important lesson why you should care about measurements and units. This is a train, and this is one of my favorite stories. It's a train in France. What they just recently did is they bought 2,000 new trains. 2,000 new trains. You know what they discovered? The trains was too wide for the platforms. And you are not returning 2,000 trains. So what you're doing in France now is they're rebuilding the platforms. Not all of them, but quite a few of them. So again, measurement is important. This one, everybody from Sweden should recognize what it is. It's the most famous Swedish disaster. It's the ship, Vasa ship, which is on a very nice museum in Stockholm. There are many reasons why this ship sank, and one of it is because it was just too big. But another example that not so many people know about is that when this ship was built, it was built as a collaboration between Swedish shipbuilders and shipbuilders from the Netherlands, which at that time was considered the best. Problem? Well, they use different measures. So if you analyze this ship, and if you are a historian, you can find things from that part of time where you have different set of rulers. You have a Netherlands ruler, a Dutch ruler, and a Swedish ruler, and they're not the same, meaning that the ship is actually asymmetric. And this is my favorite one. This is a bridge. It's a bridge that goes between Switzerland and Germany over a small river. And the problem here is that Germans measure height by height over the sea, but it's the Ostersee, the Eastern Sea that we have here. Switzerland are measuring height over the Mediterranean Sea. They knew about this, and it's a difference of 27 centimeters. Problem is that instead of canceling it, they double it. So it means that when I don't know how the story is, but you can sort of figure it out. When they actually met in the center, they had some problems. So measurement is very, very important. And people have been discovering this for many, many years. And it was actually already in 1799 in France, after the French Revolution, that they kind of learned that it's very nice if you have a standardized system for measurements. And I mean, back in the time, you had measurements often depending on the city where you're at, the country. Very often it was dependent on the size of your king, for example. So what people did then is they find out that we should have a reference that is not changing with time. If you change king, we're not going to change the size of the meter. So they defined a meter as 10 million of 1/10 of a million of the distance between the North Pole and the equator. And they managed to measure this in some kind of weird way, which is a very, very interesting story, so you can read about that by yourself. And also they defined a gram, such as 1,000 of the weight of 1 liter of water. And 1 liter of water was then a cube, decimeter cube. So everything then came back to the Earth. And of course, the purpose of this was trade. If you want to buy 1 kilogram of gold, you want it to be the same in France and in Stockholm, for example, or whatever. And this then has brought us to the current SI system that we have. It's based on this metrical system, and you are very familiar with these units. You have the second, you have the kilogram, you have the mole, you have the ampere, you have the meter, you have Kelvin, temperature, and you have candela, which is very, very confusing, so I'm going to leave that out. But this one, as it is right now, has a problem, and is that this kilogram is defined as an artifact. Meaning that all this system, especially even the ampere and the candela and the mole, is defined on a piece of metal that is in Paris. So one thing that all the NMIs are doing at the moment is they're trying to replace this. And they're trying to replace it with a fundamental constant. So I'm going to mention this because I think it's a very cool thing, and I think it's very important that you know this, because in 2018, the definition of the kilogram will change. Because what people have been doing at places that, not at SP because we can't afford it, but the large NMIs like NIST, for example, are working heavily with this, is they're trying to find a better way of defining the kilogram. And one of them is this, what's called a watt balance, which I made myself. And another one is the world's roundest object, which I also made by myself. And it's a way of actually relating then a measure to a fundamental constant. By this technique, what you want to do is you want to use what is called the Planck's constant. And with this technique, you want to use Avogadro's number. And what is the reason why I'm talking about the kilogram now is, after this change in 2018, I'm saying probably because it's not set yet, but very likely, this SI system, as you know it, with all these units, will fundamentally change, where all of them will be depending on fundamental constants. Does it sound good to you? Very good. Do you have any idea why it's good? That's a very good question. He's asking where you get the accuracy in the first place. And the thing is that what you're doing in this process is that you're using the measurements or the technique that you have today, and you're trying to measure the constants as good as you can. So that's what people are doing with the kilogram. They're trying to measure Planck's constant. In the past, for example, people spent a lot of time measuring the speed of light, which is the constant behind the meter. And once everybody has measured this to the best of their knowledge, they're just going to fix it. And that's it. And then all the other thing depends on that constant. So it's a little bit of a complicated process that you first measure it as good as you can, and then you just decide among all of the scientists and nationalities that this is it. And then from that, you can then go back to the meter, for example. And this is actually the very important thing about this. Because once you have done something like this, once you have defined something as, for example, the Planck's constant or the speed of light, you will get a system that is based on fundamental limits rather than an object. So at the moment, for example, the object that is in Paris, defining the kilogram, gives you a fundamental limit. You can't define a kilogram better than the uncertainty of that piece of artifact. So once you do this redefinition, you open up for all these kind of new ideas of measuring things. And this is very, very important, because this is once again a box that I drew myself. It makes it possible to sort of think outside this box and come up with new innovations and new different kind of techniques of measuring things better. And that actually brings us back into time, and the part why I'm here to talk about. So I'm going to go into a little bit more of the detail then about how time has been measuring and how it's evolved over the last, well, 4,000 years or something like that. In the beginning, I would say the first people that actually measured time was the Egypts. You can argue about this, but it was actually very, very important for them to keep time over the seasons in order to grow crops and so on, which was essential back then. And they divided the night and day into 12 units, hours. And you know the reason for that, by the way? Apparently they are calculating on finger joints. So you have 12 finger joints on each finger. So that's the historical reason for that. The Babylons later divided an hour into 60 minutes, which was also divided into 60 seconds. But if you think about it, until like 1600, nobody cared about the second, right? There's no reason to arrange a meeting on the second level. So second wasn't really very important until the 60s. So then the question is, and the very fundamental question of this talk, how is then seconds and time measured? It is measured by calculating the number of events that occurs. Do you agree with me? Let me clarify it a little bit. If we go back into time, time was defined by the revolution of the Earth, day and night, also the revolution of the Earth around the Sun. And this is a very, very easy thing to measure. I mean, you're measuring every time it occurs, you say 1. The next time it occurs, you say 2. And this is essentially a measurement of frequency, right? And this is very important because if you think about it, this is a very simple measurement to do compared to everything else. You're just measuring, it happened, yes, 1, 2, 3. So this is something that's very, very fundamental with measuring frequency and then time that is very easy to measure. Of course, this device is terrible at measuring seconds because it has like a revolution of 0.0001 hertz. So the frequency of the Earth rotating around itself is very low. But amazingly enough, in the 1600s, the development of the pendulum clocks occurred. So this was actually the first time that you were able to measure seconds because it has a frequency of, well, roughly a second. And if you move even further into the technology, you get what is called the quartz crystals, very similar to what you have in your arm wrists, for example. And then again, you increase the tick rate or the frequency, making it even more accurate and even more better to measure. But I would like to say one thing, that these two has a fundamental problem, which is very important when you're talking about metrology. Do you know what it is? It's not a good reference. First of all, this one needs you to actually wind it up or do something like that. It depends on the clockmaker, how accurate you can build it. Same thing goes for the quartz crystals. It can change with time, it can change with temperature and so on. This one, on the other hand, was considered to be fixed. So even though you had this kind of fancy electronics, the definition of a second remained based on the Earth because it wasn't reference. And from the 1875, where you first defined the second, to the 56, it was 186,400 of a day. Problem with this definition, the length of the day changes with time. Did you know about that? Actually, the Earth rotates slower and slower. So if you would have this definition, time will actually change with time. That means that even Earth is not a very good reference. So what people did, they redefined the second. So between 56 and 67, they defined it to be this number of 1 day of the tropical year of 1900. Problem again, it's not very practical to measure because you're defining the second or time after something that's already happened. And also, how do you measure it? Of course, I mean, it already happened. So it was like an artificial definition. But we are now in the 67th, and this was after, I would say, the technological revolution of electronics and so on. So while this definition occurred, and even before this time, people have been learning a lot about science, and during all these years, they have discovered something or developed something that is called an atomic clock. So, and this is a little bit of a technical slide, but I hope you can sort of understand it. I'm going to try to make an effort of explaining quantum mechanics and electronics at the same time here, so don't be too confused. It will be in a simple way. So, if you think about an atom, atoms are quantized, and that is essentially what quantum mechanics says, that they have discrete energy levels, quantized energy levels. An atom can either be there or there in terms of energy. It can't be in between. And if you think about, you have an atom here, and I'm going to simplify it a lot with 2 levels. So it's a 2-level atom in the ground state, and then you have an excited state. So if you have an atom here in the ground state, How the clock actually works, or this measurement, is that you send this atom through a cavity or a kind of antenna, if you will, where you apply a field, an electromagnetic field. And what does that have to do with things? Well, the thing is that energy, because this is a higher energy, the excited state and the lower state, and frequency is just the same thing as energy. So if you can apply a field that corresponds to the energy between these two atoms, you will excite it to the excited state. And to confuse you then further, you're not really doing a complete excitation. You're putting the atom here in a superposition, which is a quantum mechanical phenomenon. So in between this part and this part, the atom is actually in a superposition between the ground state and the excited state. It then goes to the second part, where it actually completes this transition, if the field is exactly on resonant with the atomic level. And then what you do here at the end of this apparatus is that you measure the number of atoms that is in the excited state rather than the ground state. And if it's not high, you can apply a feedback to this signal and change this signal lower and higher. There is a constant sort of feedback situation where you measure the number of atoms in the excited state, you feed back to this signal that then corresponds to the atomic transition or the energy in this level. That means, and this is the important part, that this frequency that you apply is actually referenced to the energy in these atoms. Does it make sense to you? And the very cool thing is then, you have one Earth, or we have one Earth. So it's very hard to do measurements on it. It's fundamental big, and it's also changed it with time a little bit. Atoms, on the other hand, and in this case, cesium atoms actually, they are the same. If you have a cesium atom here and you have a cesium atom in USA or in Finland, it's the same. So everybody can actually do this by using the same atom. So then with this technique, they have evolved something that's called atomic clock, and this is commercially available. You can buy it if you'd like to. It's very expensive, but you can still buy it. You can just call up a company that makes them, and you can buy it. And they are used actually in many, many applications. For example, we have used them at SP as the Swedish time reference. We have around 30 or 40 of them at different locations and different variations. And all around the world, I think there is a collective network of up to 600 of these clocks that are keeping the world time. You use them on satellites for the GPS system, if you're familiar with how that works. It's also very, very important for the infrastructure of internet to synchronize information and so on. So it's a very, very important commercial product. And this slide here, and if you was a little bit confused about my description, don't be worried, because it's a Nobel Prize in 1989. So this technique of doing this measurement was then awarded the Nobel Prize, Norman Ramsey. So, from 1967 and today, the second has been defined to be based on cesium. So the definition actually reads, the second is the duration of 9,192,631,770 periods to the corresponding to the transition between the two hyperfine levels of the ground state of the cesium atom. So cesium is actually the reference for the second. And so it's supposed to say 1 there, of course, but if you have this clock, it will take 300,000 years for it to be 1 second off. So if you want to go to a meeting in 300,000 years, within 1 second, you should buy this clock. But that kind of leads me into the main part of the presentation, and this question then, is this definition perfect? If the answer to that question would be yes, the presentation would be over. No, it's not. And why is that? Well, when you do these measurements, I mean, this is really, really good. It has an uncertainty of 10 to the minus 12, 13, so 12, 13 digits. It's incredible. It's much, much better than you can do in other kind of measurements. But it still has problem, and one of the problems is the uncertainty in the atom's position. We also have short interaction times and collision between atoms. And I like to explain this by, think about it, if you want to calculate the number of children on a kindergarten or something like that. If you're running around, it's very difficult to measure them. If you only have a certain time to measure them, it becomes even worse. And if they collide, so you can't distinguish one from the other, it makes it even harder. So, and the same thing goes for these atoms. I mean, you have the atoms on the first, the earlier slide, they're very fast. I mean, they're room temperature and they're very fast, even further. So you just have a very short time of measuring them. So this actually brings us to the techniques on how you build the best clocks in the world. And step one is to cool with laser. And what do I mean with that? Well, the first thing one should keep in mind is what temperature really is. Temperature is the measure of the inner kinetic energy of a sample. That is how much something is moving. So when you say cool, it's the same thing as slow down. So the idea here is to use lasers and slow down atoms. And then, of course, if you manage to slow them down all the way to 0 Kelvin, you get absolute zero. So when that's the definition of absolute zero, when everything is frozen, everything is not moving at all. And how can you do this? I mean, if you think about lasers, you usually think about things getting warm, burning, and YouTube videos and whatever. It's very rare that you actually associate laser with being cold. But the key thing is that you can use the interaction between light and matter. And there are two different ways that is very important for this. And just easily explained, there is this radiation pressure, actually first discovered when people was looking at comets, because you can see this trail coming away from the sun. And that is that light, in this case photons, I mean photons is the quantization of light, so it's the light particle. They carry energy. I mean light is the pure form of energy. But they also carry momentum, so light also have a direction. So they have an energy moving in a certain direction. You also have something that's called the dipole force, which is much, much more complicated, but it pretty much says that if you focus a laser beam and you do this correctly, and you can actually trap atoms in the focus, which is very weird, but it's a topic for another discussion. Just believe me when I'm saying it. You're focusing a light beam and atoms can get attracted to it. But how is this done in practice? Are you familiar with laser cooling? How many of you have heard about it before? 3 people, that's great. That means that you will learn something today. This is a simplified version on how it works. I'll remind you about that. So we have an atom here, and we have a laser there. And I'm going to take this laser, and I'm going to shoot it at an atom. So this is actually a photon or light or whatever, 1 quanta of light. And if this is resonant, that is, it has the frequency that matches the energy of an atomic transition, it will absorb. So it will eat the photon. And of course, since this one also have a momentum moving in this direction, if this atom eats this photon, it will get a kick in that direction. Right? Makes sense? But since the photon just ate, since the atom just ate the photon, it will get excited. Means that it doesn't really like to be excited. It wants to go back to the ground state, and so it will, by sending away this photon or another photon. And since it will send this away in this direction, it will get a recoil in that direction. Still agree with me? Pretty much? Good. But since I have a laser and I can turn it on again, and I will do so, and I will shoot it multiple times, this will happen. It will get a kick in this direction. It will get excited, and it will go back to the ground state. And every time it do, it will emit the photon, but the kick or this photon is random in direction, while the laser is not. Meaning that there will be a resulting force in this direction. Cool, right? Exactly. The only thing I've done now is push the atoms. I actually increased the velocity of the atom, which is terrible because that is increasing the temperature. But then what people discovered, and this is actually the kind of Nobel Prize winning idea, is that if you have two lasers, one from each direction, and you do something like that, you will create a resulting force in that direction, right? And you will have a resulting force in that direction. But that doesn't really do anything. There are two lasers that are fighting with each other on which direction it will actually move. But then you apply a very cool trick, which you should know about, because, yeah, it's physics. You apply lasers with a slightly lower frequency, a longer wavelength. Meaning you're detuning them, you're changing the frequency. So this laser is no longer completely in resonance with that atom. And what do you get then? You're getting the Doppler effect. You're familiar with the Doppler effect? If you have a race car or something coming towards you, it will sound wee. It passes you, it goes whoa, right? And exactly the same thing happened here. If this atom then, for some reason, starts to move in this direction, it will see this laser as closer to resonance than it do with this laser, meaning that it has a higher probability to absorb photons from this direction than this direction. This means that as soon as the atom starts moving, it will absorb photons from the direction it's moving to, most likely. And now you have something that is cooling, right? Because as soon as it moves, it gets stopped. In 1D, and only with lasers, this doesn't really work well, but you can apply it in 3 dimensions. It makes things much, much complicated. So you apply these lasers in 3 dimensions. You also need to apply a magnetic field, because if you don't have a magnetic field, you will not have a 0 point. But I'm not going to get into detail to that. So with this technique, you can build what is called an optical trap, which was Nobel Prize 97. So then, how cold does it get? Just to give you an idea how amazing this is. So if you think about having Stockholm as 20 degrees Celsius, and you have here, where I'm standing, the absolute 0, then outer space is 3 kilometers away. With this technique, with the laser cooling technique, you're getting somewhere here, like 0.5 centimeter. So by this technique, you can make artificial temperature that is millions of times colder than vacuum in space. That should be a little bit mind-blowing, I think. So, how can this technique be utilized to build clocks? Well, remember the limitation, uncertainty in the atom's position. I've now cooled them down. They're standing still. Short interaction time, again, they're standing still. And since they're standing still, they're not really colliding either. So with this technique, you can build then atomic fountain clocks. And this is a schematic on how it works. You do this laser cooling here. You trap the atoms in the center using lasers. Next step, you're shooting the atoms upwards, and they are then passing by this measurement cavity, very much as the first clock I showed you. They will expand a little bit, but not much because they're very cold. They will fall down due to gravity, and you will do this measurement. So in principle, you have an interaction times in the order of seconds rather than just microseconds. And this is actually the way to create the best clock that defines the second today. This is from NPL. This is how they look in real life. And 3 million years for 1 second. So it's kind of amazing, right?
300 million.
300 million, yeah. Sorry. I'm confused with the numbers. So, laser-cooled atomic clocks. Is this good enough? No, of course not. You can always measure better. So if you remember the limitations before, and this is very important when you're a metrologist, that you want to measure better. So if you overcome one limitation, it's quite common that you will find a new one. So yeah, it's sure, you minimize the limitation in sort of the position, the short interaction times, and also the collision by atoms. But there are new limitations. Actually, collisions is still a problem. Not so much, but still a problem. And I'm stating something here which is very, very important. It's the measurement frequency and also external field perturbations. So when you're talking about this kind of clocks, the field from the background becomes a really big problem. The black body radiation, for example, gives shifts in the atoms, and these things need to be either calculated or taken into account or cancelled and so on. But the key thing for the last part of this presentation is then this one, measurement frequency. And this is what's really, really cool, because even the clock that I showed on the previous slide was based on electronical transitions, like 9.2 gigahertz, easily measurable with electronics. But if you think about it, in the same way as by increasing the frequency from the Earth to a pendulum clock to this quartz crystal, if you can increase it even further, you can reach a better precision. And how do you do that? Well, you move away from electronics to optics. And then comes the optical revolution. So, I mean, people have been knowing about optical transition in atoms for many, many years. I mean, for as long as they know about electronical transitions. So why haven't you used this optical transition before? No one is answering. Good, then you will learn something. The problem is to measure it. Electronics you can measure with electronics, but there is no way until just recently how you can measure the frequency of, then for example, an optical signal like a laser or even lights from a lamp to an accurately enough level. And what made this possible, this revolution from electronics to optics, is actually two things. And the first of them is called an optical frequency comb. Is it familiar to any of you? Have you heard about Fourier transforms? Do you know what it is? Honestly. When I started working with frequency combs, this was actually the first time I understood what a Fourier transform is. So what people built is actually a pulsed laser. You have two types of laser. You have a continuous wave laser and you can have a pulsed lasers. And they built a pulsed laser, and they built it such that the pulses are extremely short, and the duration in time between these pulses are quite long, or at least on the atomic scale. So it's a pulsed laser, but you have a femtosecond short pulse, and nothing happens. And you have femtosecond short pulse, and nothing happens. And if you look at it in the time domain, you have this pulse, long time, a new pulse, long time, new pulse, long time, and you have a repetition rate between this. What do you get when you do a Fourier transform of this? Well, first of all, you go to the frequency domain, right? And you get something that looks like this. So instead of having this signal with pulses, if you look at it from the frequency point of view, you will get a spectrum with equal distance between all these frequencies. And if the pulses are short enough, you can do this over 1 octave. And this is very, very important. I won't go into detail, but when you do it over 1 octave, this system becomes what is called self-referenced, meaning that you know the distance between each of these lines, and you also know the distance between, let's say, this one and 0, meaning that you get a ruler of optical frequency. So if you want to measure an optical frequency, you can use this tool pretty much. You just compare, for example, this green one with something that is almost green, and you get a very accurate number on that. In practice, it looks like this. This is the system that we have at SP. And then, of course, it doesn't produce this image, but this is the way to think about it, and that's hence the name, optical frequency comb. So it's commercially available. It will cost you some, but you can buy it. And the techniques behind it and how to make this possible was a Nobel Prize. So again, you see, I'm simplifying things, because if it would be this easy as I'm telling you, I would have several Nobel Prizes. But this is actually not really enough if you want to do this optical revolution. You also need something that is good enough to measure the atoms or whatever you want to measure in the first place. So you need to have a very good oscillator, because when you do these optical measurements, you measure it with another laser. So this is also a very revolutionized technique when you're able to take a very nice laser and make it even better by locking it to an external cavity. Pretty much what you're doing, you're narrowing the line width of the laser. And this is a little bit technical, but I think you can survive that for a few minutes. So I like to compare it with, you know, if you have a flashlight, for example, and you compare it to a laser, the difference is huge, right? You see the laser as one red spot or a green one with just one color. And this other flashlight as a white light, a mixture of all light. But actually, the difference between the flashlight and an ordinary laser in terms of the narrowness of the color or the light is much, much less than the difference between an ordinary laser and these lasers. So it has a line width of, they're building it better and better, but below, easily below 0.1 hertz now. And that's 0.1 hertz on a signal that is maybe 500 terahertz. So this signal is very, very narrow. And this is very, very important then if you want to do measurements. And the way of actually seeing this is that this is what's called an Alum deviation plot. And the Alum deviation plot tells you the Alum deviation, of course, at a certain time. So the standard deviation or the deviation of your measurement at a certain point. So if you have a laser like this, you will have a uncertainty or a precision or whatever you want to call it that goes down with time until roughly 1 second or so. If you leave this laser on, it will start growing, meaning it will start drift. So what you want to do is you want to build a laser like this. This is very good to begin with. At somewhere around here at 1 second, you want this signal to be better and better in terms of uncertainty, and that's where the atoms comes in. So at this point, kind of, you want to lock it to your atoms, using the atoms as a reference, meaning that you can keep going down on this board here. And then we are at like the final sort of technical part here on how to actually build these super clocks. What you do, and I understand this is a little bit simplified and technical, is that you use this laser cooling technique. You cool the atoms and you place them here, very cool and very nice. In order to measure them, you have this clock laser or this reference laser that I told you about, this very, very narrow line with laser that you can use to then address or measure the atoms with. And then, of course, if you do this measurement correctly, you will see a signal, but you don't know what the frequency is of that signal, and hence you need the frequency comb to actually read that out. So there is the three compartments, sort of three different parts of the clock. The reference, which you can, it's like the Earth, but much better. The way to read it out, which would then be some kind of sundial, and then some kind of things to actually get it into numbers. And before losing too many of you, I would like to add something here that also solves the problem of having atoms moving even further. There is a technique that is called optical lattices, and that uses this force that I briefly mentioned before by crossing atoms, creating an optical pattern, and then having atoms being attracted to where they have a high light intensity. You can actually place atoms, individual atoms, at individual places, keeping them locked in position as well, so they're not colliding at all, which is also done amazing. And how good is this clock, and how does it look like? Well, you have this photo. It's kind of amazing. It's a real photo. So you have all this kind of laser light and doing all these measurements, and it's pretty amazing, but it's also not very simple, as you can see. And the fact is that if you build a clock like this, the best clock that you can build, there's not a single second of error in the university, the lifetime of the university. So if you want to go to a meeting in the end of the university, which you might want to do if you read The Hitchhiker's Guide to the Galaxy, but this is the clock you want.
How large is it?
It depends on the performance. If you want to build the best one, the size of these clocks are almost the size of this room, but you can build them much smaller, like the size of this desk. But it's a rapid progress, and they are sort of building it better and better, making it smaller and smaller for different kind of applications. And just to give you a little bit idea on a different point of view how good this is the Alum deviation plot. So it tells you how accurate it is at a certain point. So for example, you have the cesium fountain clock, the one that is defining the seconds today. Is this red line. You have the hydrogen maser, which is very good at short time, and you have the commercial cesium that you can buy. But all of them is in this sort of area. And making, for example, the cesium fountain better, you can do that by making longer measurements time, but you don't want to measure more than 1 million seconds because that becomes almost theoretical impossible. While the optical clocks, these two lines, are already down here. And I would actually say, since I made this graph a few years ago, I think it's actually moved down a little bit further. So we're making it better and better. And this one, which is actually an optical ion clock, which I haven't talked anything about, but the technologies behind that one and some other things was actually awarded the Nobel Prize in 2012. So my guess is this blue one will also be a Nobel Prize sooner or later, because that one is beating this one by far. As another example on why this is important, and you can ask yourself, why do you want to build better clocks? And I will come back to that a little bit later. But one thing is because you can do better measurements. And why do you want to do better measurements? Because you want to learn more about nature, for example. The better measurement you have, the better quality of the measurement, the better information you get, pretty much. So as an example of this, think about this as a very, very good clock. It's the best clock you can buy. It's the cesium commercial clock. Do you see what it is? Can you guess what it is? It has something to do with Paris? Good guess. But then, if you build the next generation of the clocks, the best clocks that you have for cesium, the fountain clocks that you can only find in certain laboratories, you will make a sort of advancement in that measurement corresponding to this. And now you can actually see it's the Eiffel Tower, right? But if you're a scientist and if you want to discover something, you know, it's probably a tower, but I would like to build one myself. You would have no idea how to build it, right? If you then build the next generation of tool for looking at this, the optical clock, it will actually look like this. So it's a progress of making things better and clearer and to give you more information. So, one thing I haven't mentioned, but which is important, is that we already today, the best clocks are better than the definition of the second. Because for these optical clocks, you are not using cesium. You are using different kinds of atoms. You're using strontium, mercury, yeah, pretty much all of them. And this means that sooner or later there will be a redefinition of the second. But the problem with this is it's not clear which atom is the best. It's not clear yet if the ion clock, which I didn't talk about, or the lattice clock, which I gave you the introduction about, is the best. Also, and this is very, very important when it comes to definition, these clocks are too expensive to build for ordinary countries. I've been trying to get funding to build one of these clocks in Sweden, and I failed. And there is actually a good reason for that, because you have to pay at least in the order of 20 million Swedish crowns to get this program up and running. And even then you will just make a decent clock. If you want to build the best clock in the world, it's much, much more. So there is still some time before you do a real definition of the second. But there is still application for this. And for those of you that works with science, on a performing science, and I mean the faculty, you know that finding funding is not always easy. So when doing this and trying to fund these kind of projects, I started out arguing that you need to do this because it's cool. It doesn't fly very well with the funding agency. And it has been very hard for me to actually convince people that it's the amazing thing you want to put money into. And I'm not sure if I succeeded yet, but I come to the conclusion it's the best way of actually doing it is to show first this slide. Optical clocks, application. Well, there are applications in physics, as you can imagine. You can measure things better. You can use it for observation, much like the Eiffel Tower example and so on. But the rest of the 4 boxes is completely empty, because I can't come up with any good application, actually. But if you then show this slide and the applications of microwave clocks and what the microwave clocks have made possible with that technology, it becomes much clearer, at least to me, because you think about it, navigation with a GPS system, Not possible without atomic clocks. Not even close. Internet, which is a famous invention, may be possible, not as fast, and definitely not wireless 3G and 5G internet. Not possible. Power grid synchronization, when people are talking about smart grids and so on, may be possible, but not very easy if you don't have this kind of clocks. And also then financial transactions. You can like it or hate it, but you do this transaction, micro robots selling, buying, and so on. Not possible either. And I can sort of argue that at least these two are very, very important inventions made possible through fundamental research with the first atomic clocks. And especially this one I think is funny, because if you look at one of the first paper where they suggested, well, you can build a clock, or I don't even think they called it a clock. You can build this apparatus that can measure things. What can you use it for? Well, you have to remember that built in the 50s or 40s even, I think. There were no sort of space program back then, but it was sort of coming along. So the first suggestion is that if you build two of them, and you place one like in Los Angeles and one in New York, you can actually use these signals from these clocks and navigate spaceships. Now we know it's the completely other way around, that you have clocks in space, you're using these signals and navigate here. So it is very hard to come up with these applications. So, I think this is kind of the last slide. Are you still awake? Are you still not amazed? So to wrap things up, the best microwave clock give an accuracy around 10 to the minus 16. That is 16 digits. You can possibly, I don't think you have made any kind of measurement on that level, not even close. The best optical clocks today is better than 10 to the minus 17. They're actually approaching 10 to the minus 18 very, very fast. And I'm not surprised if at any of these labs they're actually past that limit now, but the publications is not yet out. So it's just a question of time until the best clock reaches 10 to the minus 18 and 20 to the minus 19. Still not amazed? 10 to the minus 18. You know what that means? It means that you can measure the height difference absolutely due to the gravitational redshift by 1 centimeter. So if you have one clock on this table, and you put one clock here, and you look at them and see what time they're showing, you will see the height difference due to Einstein's relativity. And that's 10 to the minus 18. They're approaching 10 to the minus 19 soon, and there are always sort of suggestions that you can go down to 10 to the minus 21. So that means that there's a completely insane accuracy. And with that technology, I can promise you, and hopefully in my lifetime, that you will have application. For example, in geodesy, if you want to measure the height of the sea and so on. One sad thing you can do with this is you can put it in an airplane and you can fly it over the, for example, the desert in the Middle East, and you can probably see variation in gravity due to oil pockets and so on. So it's completely insane. And I also have a slide of illustration of the speed of light. I made it myself again. So the speed of light is defined to this. But I've added a question mark here. Because this is, in terms of fundamental physics, this is very, very sort of interesting. Are the fundamental constant in time? Actually, if you look at the most advanced theory of how to unify all this standard theory and so on, they claim it's not. I mean, they need to have a variation in fundamental constants. So with these clocks, it also becomes a very interesting scientific tool to measure, well, other fundamental things like constants. So it's likely that if you see a variation, it will be using this kind of techniques, because this is by orders of magnitude better than anything else we can measure. So, thank you. The question is how this relates to relativity and time, and what time you are measuring. And it's a very, very good question. I would say in order for time to make sense, it needs also to be distributed in some way. So that if you have one of these clocks, what you actually measure, you are measuring the frequency of that particular atom at that time, at this table, for example. Then you can use this frequency measure and translate it into time. And for example, you wait for a certain amount of events to happen, and you call that an hour. But as I told you, I mean, it will be different from this part to this part, and we'll be sure. I mean, you see this already, and this becomes a problem because everything is synchronized. So, for example, in US, you have the best time labs. It's in Boulder, Colorado, which is not at sea level, and it actually is noticeable different due to this redshift than in New York, for example. Sorry. So 1 centimeter. If you want to distinguish the centimeter on a centimeter level, you need a clock in 10 to the minus 18, which you already have. And people have done very interesting experiment where they put it on a table which you can lower and higher, and you will see the difference. It's quite amazing. Exactly. The remark I would say is that gravity is not homogeneous, and then time is not homogeneous either. And it's exactly it's a very, very good point, because I'm not a geodesy kind of guy, but they're putting a lot of effort into making a unified picture of Earth. And if you Google it, you can see pictures of how the Earth looks like in terms of gravity. And because it has different kind of stones, I would say, in structure, it's not as round as you think. So I would say this clock is actually very important in order to unify this, because it becomes an absolute measure on gravity, actually, rather than sort of combining these kind of measurements. And it will be the best way of measuring gravity. The problem, of course, is building a clock on this level and driving it around doing the measurements. That's not very easy. I should mention that another reason why you're not using this clock as a definition is, even though all these millions being put into this technology, running them for a long time is extremely hard. So if you go back to this slide, where you have measurement time here, it's not because scientists are lazy that they are stopped measuring after like 1,000 seconds. It's because it's technological almost impossible at this point. I think you can go down to maybe one step further and so on, but so these machines are complicated, but they're getting better and better, and I wouldn't be surprised that you can buy them commercially in maybe 5 or 10 years. This machine is actually doing exactly this. It's a laser here, and what the laser is doing, it's creating these pulses. It's a pulsed mode-locked laser, which I'm not really an expert in, but the key thing is producing a laser pulse like this. So what comes out of these lasers is these pulses. But at the same time, if you can look at it that fast, the signal looks like this. But if you don't care about time, if you observe it over a longer time, it looks like this with these discrete levels. So what you're doing in order to make it fixed, which is very important, this repetition rate, or the time between pulses, you're using regularly electronics to lock it. So you have a detector that measure the pulses. I have a pulse, I have a pulse, I have a pulse. And you want to make sure that the repetition rate is then fixed. Because if it's fixed, the distance here becomes fixed. And the repetition rate is typical in 250 megahertz. So that you can actually measure and do with electronics. And then it's getting more and more complicated. But in order to make sure it's exactly 250 megahertz, you can then use an external reference, like another optical clock, for example. So it's, besides being this amazing tool for measure frequency, it is also a tool to go from electronics to optics. So you can transform signals in a beautiful way. Yes, very good question. The question is what kind of frequency or color or wavelength it is. The COM that we have at SP, and that's for reason that there are very readily available components in telecom, it actually centers around 1550 nanometer. So it's a telecom wavelength. So it's twice the visible light, more or less. But then there are techniques, nonlinear optical techniques, to double this frequency, or half the wavelength, transforming it actually to the visible spectrum. So that with this particular one that we have at SP, and this is the commercial and most commonly used one, it goes, I think, produce frequency or light from all the way down, not really in the ultraviolet, but maybe somewhere there, up to 2000 nanometers. Now, what you will get out of this actually is you will get a laser beam after all these nonlinear things that looks yellowish. But if you then take it to a grating or a prism, it will actually split it up. So you will actually see a laser with all the colors in it, which is very confusing to people that is used to a laser with one color. But then people are doing advances. I mean, this is a research field, a big research field in itself. So people are doing a lot of research trying to get down to the ultraviolet and even X-ray comms and so on. And actually the most interesting things for frequency comm is up in the mid-IR, where you can use this system to do laser spectroscopy, detecting gases and so on. Yeah. So the question is how much better this measurement in terms of the SI units than the rest. It's a good question. One thing is that in practice, the meter is actually the same, because the way to define the meter is by measuring using the fundamental constant of speed of light and then measuring second. But it's very hard to translate that into a practical measurement. I would say, I think it's like maybe close to 9 or 10 orders of magnitude better than all the other practical realization. I'm not an expert, but getting down to parts per billion is very hard in all the other aspects in reality. So this is way better. I think you can do with the resistance and the voltage and so on, with this quantum Hall and Josephson junction. You can probably do better, but you have to remember that these definitions is actually based on the kilogram, which has a fundamental kind of limited to parts per billion. So it's a little bit complicated. This kind of discussions is interesting, but I think it will also confuse people, and the risk is we get a new Mars climate orbital failure. But the kilogram is weird. I mean, it has this prefix that all the other units doesn't have. I was actually confused by that just a few days ago, because I heard I was calculating the uncertainty of what 10 micrograms is of the kilogram. And I forget about the prefix, and it can't be right. I mean, but, oh yeah, I need to add a factor of time. Yeah. That is a very, very important question. So the question is, how do you calibrate your clock towards these kind of clocks? And I would say you don't. And the reason for that is you probably don't need to do that. And also time is something that, and this is very, very important for us at SP, that we are not only keeping the time, maybe more importantly, we're distributing the time. So we may want to make sure that the signals that you can get from the GPS system, for example, which is a very good way of getting a good time, or the internet, like the NTP protocols. So this is actually the main part of what we're doing. And on that level, you don't need 10 to the minus 18 in the next few years. I don't want to be absolute, but so these clocks are more like a science machine than a clock itself, because fundamentally you're not running it as a clock. Because if you want to have a clock, you need to start it, and you need to sort of observe it all the time. So mostly what we're doing is we have a lot of clocks, not on this level, but we want to make sure that they're running all the time, keeping the time in Sweden and so on. But I mean, if you, for some reason, I mean, it's possible, of course, to take if you build another machine, and this is what people are doing. I mean, in order to know that you are 10 to the minus 18, you need to compare it to something else, which is the problem. So people are often, that's one of the funding problems, that you need more than one clock. So if you look at the other labs, they're building multiple clocks, 5, 6, 7 of them, and comparing how they perform in different regime and by different sort of limitations. Because you can't say that I have a clock that is 10 to the minus 18 without being able to prove it. And that's also another problem, is that in principle, and this is an argument, that if you see an article with people claiming that they have an accuracy of 10 to the minus something that is below than the definition of the second, that's fundamentally wrong, because you can't be better than that definition. So to be honest, I mean, the best clock as a clock is the definition of the second clock, I mean, based on cesium. The answer, and the question was how much better can the GPS system be if you build better clocks and put them in the satellites. And the problem is that at the moment, the GPS sort of navigation part is not really limited by the clocks, but rather by disturbance in the atmosphere. I still think it's interesting because if you build better clocks, you probably can learn more about disturbance in the atmosphere, but you don't really know. So it's, I wouldn't say much better, but you can definitely improve it. And maybe more interesting as a completely new applications is that you can measure atmosphere and, I don't know, greenhouse gases and whatever interesting thing. So it's another, I would say it's another kind of application. The question is if you can buy time. The thing is that, I mean, I would say in terms of time, we have what we need in Sweden. And there is no point for me to have better time. I mean, it's the frequency measurement that is important, and also the science behind it that is attractive to me. Building it as a time device is not what you want to do. You want to build it as a science device. And even then, for me then personally, you're getting into problems which I completely understand from the funding agency, that NIST and PTB are so much better. I mean, already. It's very, very hard to build something that is even close to this. My argument is that I think this is such an important technology, so just for the sake of having this knowledge somehow in Sweden, it makes some kind of sense. Because you can also do a lot of, I mean, the way forward, I mean, it's not only measuring the time, because you have the black body radiation that you can do measurements on, and you have dipole moments of atoms and whatever. I mean, the technique is very, very utilized for many measurements. A lot of people are building clocks for another purpose in measuring time, because they're interested in measuring another shift of an atom and so on. But building this is a very ambitious project, and I would like to do it, but I don't think it's feasible in Sweden. And I'm not too upset about it either. Okay, so the question is there an intuitive way to understand what time really is? I don't know. I'm not the kind. I don't think I'm the right person to ask. I would say increasing entropy maybe is that's the direction of time, but it's a too philosophical question for me.
I think we can stop here. I think we could continue for another hour or two talking about time and other things. But we would like to, from the organization side, to give you a little bit token of appreciation.
Thank you.
Thank you very much.
Thank you.